I'm Hana, and I'm chair of Czech National Body in C++ committee. And also I'm chair of Reflection Study Group, which is currently doing nothing because no one is sending papers. So if you want reflection, you need to send a paper. And also I'm a researcher in Avast, working on various stuff. And maybe you know me for CTRE library. How many did see my talk or know about the library? Okay, so you probably know me, kind of. Okay, so the problem for this talk, I'm going to talk about update system. And the problem is, in Avast, we have tens of millions of endpoints. And I want to update them quickly every few minutes. And I'm going to talk about that. So about the code examples you are going to see, they are in C++23. I made it specifically in 23, even when the library is in 20, to show you some features in language. It's a slideware. So the code probably won't compile. And there is a lot of things which are not presented, because I don't have time to present everything. But I try to distill only the important things. And also, all the code namespace is in Luna, because I like the name. It's not about the crypto coin, which is terrible. So sometimes there is a namespace, sometimes there is not. Depends on how I fit the slide or not. So, Lightning updates. What can you update if you have an application? You can update an executable. Most people do that. Or most applications do that, because you want always the most recent one, secure one. But usually you update content, database, textures, models, you name it. But actually it's a state of the application itself or part of it you're updating. It can be database, it can be some internal configuration. So the state of the application is actually immutable. It cannot change. It shouldn't change. Otherwise, from the outside, from the updated system. It should be consistent and secure, so no one will meddle with it or it won't get broken by some random error. And it should be representable as a data structure. It can be stud map, it can be dictionary, it can be vector, it can be anything, but it's a data structure. And data structure can be represented as a file. Most applications store data structure, what they are updating in a file. And it contains your data. It can be a new game. It can be database. It can be, again, anything. But the data structure itself is subject of the update system of this one. But generally, every update system is changing a data structure. Maybe they just don't know that. Oh, sorry. Updating mechanism usually can replace everything. You download new version and replace your app with new version. That's the simple one. You can have additional or overlay layers, which create like this. But that also creates some errors. Or it can be differential when you're applying patches. That's the most, I would say, cheap one if you count on your, measure your traffic. So generally speaking, if you have one state, you can get to next one if you apply difference between them. Makes sense. And difference can be like shown in a matrix between states, so you can see from which version you can go to which version. But it can be also an update graph, like this one. You can go from A to B, from B to C. Something is not right. Okay. And then to D and to E. But this is really simple. You don't want your user, if you are creating a lot of updates, to go from many small updates. You want to update them as fast as possible. So you start again. We have A to B. And we can create shortcut between states. You can do them algorithmically, like every day you will create a jump 1 week back, or every hour 1 day back. Or you can measure it if you have some telemetry. You can decide how many users are on different versions and create the jump for them. Or another jump. and another one, or even bigger one. There can be there can be virtually unlimited number of jumps if you want, but actually it costs to create every jump because it's computation and space on your CDN or some storage. So you shouldn't do that for every version. You should do that only for the recent version, like on the matrix. So if you are in state A and you want to go into state E, the path is obvious, the short one. Just take it. Okay, what about A and D? Maybe this one? Okay. And what about between B and E? How do you find path between B and E? Because your application cannot see the graph, because the graph with time will grow exponentially. Information about the graph and connection should be stored somewhere in the version itself, maybe like this. But you actually cannot predict future, so you don't know what will be future update. So you need to store it in future and go back into past. So the nodes are like ordered by time. And how do you select the best path if you know only about these 3 nodes connecting from E? You look for the node, for the path leading into node which is closest to your target one. And then you download it, and then you see there is a connection from the downloaded one into one you have. You connect it and you have a path. You can, in a reverse, apply and get the latest version. Okay. So how do you represent the link between states? It can be a file name with a version number or name of the release, but it sounds manual, like manual labor. And if you are doing high-frequency update, you cannot do that. Even better is have an identifier depending on its content. It can be a hash of the content. And hash value then became a pointer. It gives you unique value for its content. So every time you change it, you will get new hash value. It's called content-addressable storage, which is used by Docker, for example. Every time you change something, it will get a new ID. And that helps to make software which is reliable and repeatable, with repeatable results. Also, storing your content under its hash makes your data immutable. You cannot change them. So you can also really easy cache them on CDN or on some storage. So you can distribute them around the world, and you know that they will never change. And also it gives you transitive trust. It's like hash chain technology, not like blockchain. Blockchain is terrible. And so we have various states from the previous path, BCE, as I showed on the graph. They were states, not the diffs itself. They are connected, but it's just state. It's not actually the content. It's just description of the state you are supposed to go. Description means there is a identifier or some like maybe hash again of your subject you are updating. That's the data structure you are updating. And between them, there are actually another objects, deltas, which are containing delta between various states. You need to apply to subject B to get into C and so on. They also should contain the information about previous state. It's easy to just copy the state itself because it's just small, just a few hashes, that's all. And some of the nodes can actually contain a link into snapshot, which is serialized version of the subject. So you can get subject by unpacking the snapshot. You can get subject by, if you already have a subject, by applying delta and the delta again. And you can also get subject by unpacking snapshot and applying delta and delta again. So not every node needs to have link to snapshot. Just can go into history and find the closest one. Okay, so we have a graph, state A, B, C. And let's say we want to update into B. We don't have anything. You need to download, because there is only one way to anywhere from DB. We will download this div. And that way, we also have state E. And state E contains a link to snapshot, which gives us subject. And then if we apply the div, we get subject B. Okay, so we now have the problem described as a graph, and we need to model it as a C++ code. And hash can be just a bunch of bytes. It's like crypto hash is like 32 bytes if it's SH1, or 16 bytes if it's SH1. Oh, yeah. So we can model it like this. Hash is that array of bytes, hash view is span of bytes. Are you okay with this? Raise your hands. Okay. Technically, it will work, but your code will get complicated, and in time, there will be probably bugs, because you will have multiple of spans describing bytes. Once it's a hash, once is content of the file, anything. So we should do strong typing, implementing by proxy. So we have hash, which contains array, and there are a bunch of constructors. You need to ask for it for comparison, begin, end, so you can iterate it, non-const iterate it, and also hash view, same thing. It's just like proxying everything. There is much more, but for slideware, it's just few functions. But better is use inheritance. Take a type and just inherit from it. And it will give you everything you need. It will become a range. It will be comparable. You don't need to write a code which is already given to you. And it's totally fine. And I need to say, maybe it's UB, but you don't care. But you shouldn't implement your destructor and add a new member, because then a U type can get sliced. You don't want to do that. And then I'm naming the parent type super, and with using super, I will bring its constructor to the same level as my constructor, which is next. So they are on the same priority level. And this one is explicit and initialize the storage from the view, hash view. I cannot use the ranges 2 because it doesn't work for arrays. And we should thank that to the committee. I don't know why it's not working. So I'm using uninitialized copy, which takes the view and copy it into uninitialized storage of the hash. And hash view is same. It's span, immutable one. And I'm doing exactly the same, but the constructor is implicit, explicitly, if you like that. And you need to specify comparison, because span in C++ is not comparable, because Tony didn't want it, and convinced the rest of the committee it's a bad idea. So you need to implement your operator UFO, and with algorithms for that, and operator equal. Because committee in late in C++ 20 cycle decides that you should implement both operators, because comparison of operator for equality can be much more complex than equal. So it's faster to have both of them. And then we have tagged hash. We can continue, which inherits from hash, which is just small layer on top, which gives a new meaning to type. It adds a new constructor, which calls the previous one. And we have tagged hash view, which is exactly the same. It's just small, thin layer without any code, actually. And then you can implement your tags describing various hash functions. And then you can implement strong types for your hash or specific crypto meaning. Okay, and if you implement it properly, you will get these rules. So you can always implicitly convert from value to view, not back. And you can always convert from more specified version to a less specific version. But explicitly, you can go back, but explicitly, it's much, it should like pop out from your code. So explicitly, otherwise, it's harder. Okay. Tony asked me to place this code here because Tony is Tony. Anyway, so sorry. Yeah, and now when we have pointer, we need to describe the rest of the graph in types. I will start with the metadata type, which represents this state. Metadata type contains always hash of the subject you are updating to. Like you are supposed to be in this version, not in that, on this specific version. Then there is a color of graph. If you have multiple graphs together, so you can detect if it's state from different graph, such as like there was some history behind that. And there is also timestamp when the node was created. And there is a rule that every time you create a new state in graph, it always has bigger timestamp than the previous one, than all of previous ones. And previous ones are described as delta link, which contains timestamp of the previous one, identifier or hash of the delta connecting to previous state, distance to closest snapshot, how many jumps you need to take to get closest snapshot, comparison, just defaultly. And there is a list of the links because there can be multiple links. And there is optional link to a snapshot. Not every node has a connection to a snapshot. And also I have added a few values which are not serialized. I used like these dummy attributes. Let's say we have protocol buffer implementation which looks on the attributes with reflection and decides that these won't be serialized. Just like it's a slide var. And there is a hash of the state when it's serialized, and also the original serialized version, so you can access it later. Yeah. So now we need to like describe delta type and snapshot type. Delta type is just metadata of previous state, and a vector of bytes containing the patch without any meaning. And snapshot is just serialized version of the subject as a content. So now we need to implement identifier, which is just hash of some specific meaning, and a type of the object. We can compare it against the type with a hidden friend. It will pop out in your overload set only if one left side or right side is exactly this type, otherwise not. And also operator / which will help you nicely serialize your identifier into URL where you will download the object. Just like take your prefix /ID and you will get the name of the file you will download with concatenation and some encoding. So we have type, enum class type, which is metadata, snapshot, delta, and alias. Because if you have a graph, how do you say to your user how to find the latest version? You mark something with a copy of metadata under different name. It's no longer saved under hash of its content, but under its name. And it can change. So every time your application checks some specific name, it will get new version, which is just copy of some state. So we can have different version for beta, different version for stable. And when beta is stable enough, we can just take it again. Okay, alias is just copy, as I said, of the metadata stored under name. But it can be hash of its name, because everything is hashed and it's nice to have symmetry. Also, because it's a different type of identifier, with different extension or how you implement it, you can specifically change rules of your storage, so this file won't be cached aggressively. Let's say TTL 5 minutes, if you expect update them every 5 minutes. So client will download some bytes and needs to get an object. An object is, there is type, any object which is just inheriting from variant. And I'm doing exactly the same. And because for reasons I will tell you later, I'm not using stat_visit, I'm using getIf, and I just wrap it. So I'm asking is this object metadata? If yes. And I'm also using deduce this. How many know about deduce this? Okay. Deduce this is ability to explicitly ask for type of implicit type of your when you're calling member function. First implicit type is this. So you can deduce constness or type and implement much more like the recursive curious template pattern. I think it's now called. So I ask if it's metadata. And thanks to deduce this, I don't need to implement a const version of these functions because they are implemented for me, because these are actually templates, because there is auto. So constness of this is deduced. And so on. So now we need to somehow crystallize them. So this is quite longer talk. When we somehow get an object somewhere, we provide, we already know its identifier, and we got its byte. So let's say identifier byte, and from this function we want to get the object. Let's say there is a protobuf format a wrapper which contains object type, metadata delta snapshot bytes distinctively, and additional signature. So we deserialize it, the wrapper. And if we ask for metadata in identifier or alias, we check if the type match. If not, just throw an exception. And also, if we ask for metadata, there should be metadata bytes, obviously. Then we calculate hash of the whole metadata bytes we are using. And if type was metadata we asked for, we can check if the hash expects with the data we are getting. If not, it's damaged. I'm not doing the check for alias because alias cannot be, because we don't have hash of the alias ahead, so we cannot do check for the alias. But then we need to check there is a signature, because every state should have signature. If not, there is missing signature. And then we validate against some trusted keys from somewhere, the hash against the signature. And if it doesn't match, we throw exception, which means from now on, we can trust every state we get because it's signed cryptographically. And because there is a transitive trust between objects, we can trust whole history from it. And then we call some type of metadata function, which takes the hash, metadata bytes, and bytes of whole object, serialized in serialized form, and do something with it. Then if we ask for delta, and the wrapper is not delta, obviously error, and if there are no data for delta, error, but also data contains the metadata or state previous one. So we need to check for that too. Then we calculate a hash of both bytes, blobs of bytes concatenated together, and compare it again if it's correct. And then we call prepare delta with delta bytes and metadata bytes. Okay. And if it's snapshot, we do the same with the type. We do the same with the check of if there is actual data. We do the check of the hash, and just materialize the bytes of the snapshot into from view into value and return the object, because we were working with spans. Otherwise, if there is anything else, it's just invalid object. Okay, so then we need to prepare metadata. We take hash. We take bytes of the metadata, and they are still not deserialized. And if we provide it, also bytes of whole objects serialized from whole wrapper. And we will return metadata. We will somehow deserialize it. I don't care how. It can be JSON, it can be protobuf, it can be XML, it can be Markdown, but just don't use YAML. Then we store its hash. That's the reason I didn't serialize it, because we cannot know the hash of serialized content before we serialize it. And the hash would change the serialization value. So. And then if there is a wrapper, we just take the wrapper from the optional and again materialize it with ranges 2 and return results. So it's preparation of metadata. Delta will take delta hash, delta bytes, and metadata bytes, and return delta. It will calculate hash of metadata itself and call function prepare metadata, but without any wrapper, because we don't have actually a whole wrapper with signatures, so we can provide them, but there is no signature with it. And I don't want to like serialize it again, because there is a space for an error. So I prefer to just copy the bytes itself. Anyway, then I will take patch against materialize it into values, and then I return delta and fill the object by name constructor, because it's just simple structure. Yeah. Then there is update algorithm, because now we saw for all the vocabulary object, but now we need to do something, to have some verbs. So we have update graph again, which exists abstractly as an object in some storage, and we need to transform it into memory. We are in state C, and we actually have the subject C, so application is okay. We just point at the state C, and state C is just some type state, and subject is some object, like C++ object. So let's say we have pointer from application to state, and from state there is a pointer to subject. And when we update, we change it to new one, and again to new one, and so on, so on. So there's the connection between graph and the structure in your application. So state type is just storage metadata, deserialized one, and subject. But actually, it's not the value of the subject, because it can be big and it will be shared. So it's a shared pointer of const t, and t can be anything. How many people don't like using shared pointers? Okay. And there are some functions to get hash, color, and timestamp from the metadata of a state. But shared pointer, generally, it's not great, but shared pointer of const t is actually awesome. By the way, Sean Parent said that, so it must be true. It cannot form a cycle. If you create a const t shared pointer, it will never create a cycle. So it won't never leak. So that is the biggest problem of shared pointer. If you create a cycle and you have a leak, this cannot happen. And if you are actually sharing something, it makes sense to use type which has shared in its name. Also, if it's const t, it's actually no longer a referential type. It behaves as a value, just a value cheap to copy. So if you provide shared pointer across your application, you don't need to have any locking, because the t will never change. Also, it saves memory if you deal with large objects, and usually in update systems, you deal with large objects like 100 megabytes. So we have state, and now we need to create an algorithm how to find a path in graph. So let's say we are in state B, and because we are in state B, we know that there is a connection to state A, but we want to update to state G. How do I find path between G and B? I first download it and got the state and its information and its connection to previous states. So I can choose the node. In this case, I will choose obviously the one which is closer with timestamp, which means more on left, to B. So, okay, but there is still no connection. Only connection to A, which is predating to B. I cannot choose that because some of the differential functions can work only one way. So I will choose C, and there is a direct connection to B. So the algorithm is actually easy. You just walk your graph and find the node which is as timestamp higher or same as your like node you already have. But the graph actually was much more complicated, but you didn't see it, and you don't need to see it. Okay, so how we select next? We take metadata, the state, and we take shared pointer, reference to shared pointer, to current state, and a return identifier of object we want to download. So if we do have a state, it's not null, and our color match. If it doesn't, we mark our state as no longer necessary, and we are switching from searching path to our state. We are now searching for path for whole update to like reset. If we still do have a state and timestamp is in history, so we are actually asking to update the application to something which is predates current state, we need to do full update again. Also, every metadata should be built that there is a snapshot link or at least one delta to previous state. So if we are not in a state, like if we are searching for path and we don't have current state, and there are and if delta links are empty and there is a snapshot link present, we just use it because it's the closest one, closest snapshot we can get. So we download it and we are done. But if we are in a state, we can take all the links, filter them with range view filter, and there is a function which filter only eligible links, which are based on delta link, only with timestamp greater or equal to current timestamp of our state. And then we look for the smallest timestamp, because that's how the delta links are sorted defaultly. And we will take its hash and build identifier to delta object, and we will download it next. If we are not in a state, so we need to do full update, and there is a snapshot link present, we look at the delta links, we compare, we look again for something minimal, but compared with less, and we use projection to compare them against distance to a snapshot. So we will look for the closest path to closest snapshot. And then take its hash and create an identifier and tell application to download it. Okay, so we have, by applying this, we can get a path of any objects we ask for. And now we need to somehow get the objects. How do you get object if you have only identifier and the object is on some sort of CDN somewhere, I don't know, in Iceland maybe? You use coroutines. So there is a function, convert to object, which takes identifier and other coroutine, which takes vector of bytes, which gives vector of bytes, and a return task, returning any object. And the async fetch concept is defined like you can call it the fetch bytes, and if you call it, it will give you available with the result you're expecting. In this case, vector of bytes. So you will ask some coroutine, please download me this bunch of bytes with this identifier. So you can use the operator slash to get its URL, download it, and when it's finished, it will unwrap and validate. So it's the serialization, all the checks, and it will return asynchronously. There is your object, or there is an exception. There can be an exception. So we can then later implement some sort of download function, which we will use maybe a libcurl, or on iOS there is like fetch content. It can be like it's your native function and it's on your platform, and you should know better than the library. So the library shouldn't do the actually I/O for you. It's your job to implement it. Okay, how do we fetch whole path? Again, we have a shared pointer, now by value, not by reference. So we take copy of current state. There is a type hash or name, which is just variant of target hash, updating to or a string containing name of the target. And then function, which will provide any object for you and return vector of objects asynchronously. So we have a vector of objects, that's our result. And if we have a state, currently one, and state's hash is same as our target, obviously we don't need to do anything. There is no path between here and here. Otherwise, we convert the target into identifier. So it means calculating hash of the name if we provide name, ask to fetch the object, wait for it, and then place back on a vector. And then we will repeat something. Every time we look on the last part of our path. And if the last part is metadata, and I'm using get metadata, the get if internally, because in this context, using stat visit will create a new function, and you cannot await or co-yield or co-return from function which is not coroutine. And it would make the code much more complicated. So this is much simpler. And remember, we don't need to optimize this because we are actually downloading files from internet or from somewhere. So we don't need to optimize few instructions here. So if it's metadata and we are in state, we can check if the metadata we just got are current state. If we are connecting to current state, as we were walking through the graph, we just return the path because we finished, we arrived to our target. Otherwise, we call function select next, which will choose which next node we should take, fetch the object, wait for it, push on the path again. If we got delta, we just take the previous metadata from the delta itself and place it in our path and repeat again. And if we got snapshot, we got it only in case when we are doing full update. So we return the whole path because we don't need to do anything else. So we can have state, version m, and it's just state n plus path applied in a reverse. Because as we are going from the future into past, we need to apply it from past into future. If you do it in other order, it won't work. So it can expand into First, we download always metadata, alias or state, apply delta, 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 and then we have the previous state, and you can call it a day. So it looks like this. We have current state, which owns a subject. We create a copy, and then we take a delta from the path, apply it, we will get new subject, slightly modified. And I recommend, in this case, use a subject type, which is copy on write, but that's just optimization. And then we got new subject. And again, new delta, other subject. And when we are done, we just mark it as new current subject, and we did the whole updating process. So update state is actually quite simple function. We have a reference to atomic shared pointer. So we can actually load it and store it atomically across threads, which is useful in this case because we are updating and the state can be used across like whole application. We have target where we are updating, and we have asynchronous fetch of bytes provided by user, and a return update result, which is just variant of like saying what's the result. So fetch object is just a lambda which takes the callable, which returns a task of bytes, and call function convert to object with identifier. So the function doesn't need to do it for you. But this lambda is not a coroutine. It just wraps together, and every time you call it, it creates tasks from different coroutine, and you can await for it. But this fetch object doesn't need to be a coroutine. So there is no co-return, but it's just normal return. And then we load current state because it's atomic variable, so we load it. And then we fetch path between old state to our target of our update with, sorry, there is a typo, it should be fetch object, not get object. Sorry to confuse. And we download it and then when it's downloaded, we need to await for it. Then we pipe it into use fault write, which is just accumulate function on reverse iterators, and we will fault against old state. And that's how we got new state. But I don't want to implement D plus operator for old state, so I have some functor, apply, and there is something called update traits. And when we finish, we got new state, and if there was previous state and new state and previous are equal, then we tell user we updated to latest version, so we are already on it, so you don't need to do anything. But otherwise, we store it atomically into current state. There can be some copy and compare, store and compare, and then asynchronously return update was finished successfully, and there is new state also, by the way. Okay, defunctor apply is just helper type, which takes its template, which takes parameter update traits, which must be compatible with your type, and inherits from them. There are some to make it shorter, the slides. And then there is operator call, and every time you have a snapshot, it calls the operator call against state and snapshot, and it will give you new state. In this case, it's just deserialize the snapshot bytes, which can be stealed from, so there is no const in the reference. And it gives empty metadata and creates new state and gives it to you. And if it's delta, you just take previous subject you already have in previous state and apply delta. You can also steal from it, apply it whole patch somehow, and with empty metadata, it will give you state. And then if you got a metadata, new path, which will be at the end of the for link, it will calculate hash of the subject, compare against expected hash of your subject, And if it fails, there's something wrong with your update system, but it shouldn't fail. And at the end, it will create new state with same subject as previous one, but with correct metadata, which is valid state. And that's kind of all. And update traits, let's say, looks like this. We have calculate hash function, which takes subject type and return hash, or calculate difference, which take one subject and other subject and return some sort of patch. I don't need to understand it because that's specific for every subject type. Apply difference takes previous one, takes the diff, applies and gives you a new subject. Serialization takes subject and serialize it. And the serialization takes serialized form and a return subject. For example, for BSDiff, if you know a new BSDiff, you can just calculate hash is just take the byte, calculate SH256. Calculate difference, just call some sort of like magical function BSDiff into vector. Difference is just apply patch into vector. Serialization is just, I will take the serialized version as a view and materialize it as an object. The serialization is exactly the same in other direction. So that's the internal and how user will use such library. You have like, when you are updating, there can be some problem. And the reason why I'm using share pointers is when you are started some update process, and meanwhile, there is a task in your application. In my case, it's antivirus, so it's doing some scanning of your files. And it's long-term task, so it takes reference to subject and do something with it. But meanwhile, the update process is running. And when it's finished, suddenly the task has dangling subject. And you don't want long-term tasks suddenly be dangling. That's the reason I'm using share pointer, because I'm actually sharing. And then can be another task which can start working with new subject. But the library shouldn't decide for you as a user if the task one should be canceled because we updated, or maybe it's okay to let it finish. So user API looks like this. We have, it's a template, live value, which takes type you are updating. In BSDiff, it's vector of bytes. Traits compatible with the type. And you have state, atomic shared pointer. And then you have a function update to, which is similar as one I show you, but as a member, so there is no reference to atomic shared pointer, which returns results asynchronously. And there is a function get, which will give you shared pointer of t, not the state, only t, because user cares only about the subject, not about the state and everything. So we load a current state. If there is none, null pointer. Otherwise, we will return the share pointer from the subject. So there is a share pointer in share pointer, but they will never create a cycle. Okay, serialize current state. Just gives you some sort of persistency, because your application should be able to store its data every time it's updates, or maybe some like every hour, depends how often you do that. So there is it will load current state and call function serialize state, which takes the share pointer, so it can hold it. Again, share pointer is useful. And it will give you a vector of bytes. It works somehow like this. If it's empty, it throws exception. There should be a metadata containing original bytes, which will always happen if in correct state. And we just concatenate metadata bytes and serialized subjects together and call it a day. And then the serialized state takes optional view of bytes. I will show you later why. And return share pointer. If we didn't provide a byte, obviously we return null pointer because we cannot return anything. Then we somehow split the metadata from the subject. That's not like the content of the tool. And then we create a path from snapshot, from the persistent state. And we actually deserialize the metadata and get a metadata object here. And then we can just fold it against null pointer and get a new current state which was stored. So I don't need to write some new function, just use facility I already have. Then there is a constructor, defaultly it's empty. And then there is a constructor which takes optional of bytes and provide it to the serialize function and store it in current state. So, and it's used by user like this. You have function, some application, which is the life value of, and let's say we're updating map of strings to strings, some sort of configuration. And with some traits which provides a map updater. It's called simple database. And at start, we try to load file content from some config bin or something. And if we are successful, we will return bytes. If we are not, we return empty optional. So application can start with previous data or not. Then there is a lambda, which is a coroutine, and I have typo there, which start the update process to latest version, wait for it, and if it's a successful update, not just you're already on latest version, then it will store to the config bin, and that's all. Then at the start of the application, it's good to initialize update just to be sure you are on the latest version, and wait for it, maybe. And then if you have some sort of scheduler in your application or task manager, you can plan that every 10 minutes it will try to update to latest version. And every time you actually want to do something with the subject, you just ask for its handle and keep it as long as you need to finish your task, whatever you are doing. So at the beginning of the talk, I told you how I need to synchronize a database of tens of millions of clients every few minutes. Actually, I'm not going to tell you how, but you can change the problem into something simple. In this case, all updating is done on client, and now my task is I need to distribute a small hash to tens of millions of clients, which is much simpler. So what I showed you today, how to model your algorithm, model an algorithm into a code. And that strong types can help you build easy code, easy readable, and a reason to about. And also programming with C++ is obviously fun. And various use cases for this can be, in my case, distribution of AV signatures across the whole user base. Because every time we detect some new threat, in just a few minutes, all our users can be protected thanks to this. Also, we can synchronize configuration across cluster of thousands of computers, or distribute machine learning models to endpoints to keep privacy. So we actually won't run anything on backend, but on client, which is great. And many more. And some of you probably guessed where I'm heading. Let's say we have virtual file system, really simple one, map of file system path into vector of bytes, and traits, how to update it, which calculates hash of every name and its content and return as one global hash. Or calculate difference by iterating through both maps and looking for difference. And if it's additional, create a patch with additional for key and value. If it's removable, add the removal into patch. And if it's assert, if it's change, just use BSDiff traits we already have from different code and implement the differential function for the content itself. And then it just serialize the patch, compress it, return it. And then we can apply it. We have subject and patch. We will decompress it, deserialize it. If it's invalid, whatever. We copy the subject with auto something, which will give you copy of the object. And apply change on it. So if it's addition, we insert value into mod. If it's removal, we erase the value from the mod. And if it's change, we just apply the difference with bsdiff. And yeah, and when we are done, if there is like a missing comment with broken diff and so on, serialization is simple. Just serialize the whole VFS into some object, compress it, and return bytes. And the serialization is just opposite of the process. And that's how you make simple Git. Thank you.